Hello students, from today we are going to start the videos of real analysis 2. First chapter is Riemann integrals. First chapter is Riemann integrals. First we see sets of major 0. A subset E of R is said to be of major 0 if for each epsilon greater than 0 there exists a finite or countable number of open intervals In such that E is a subset of union In and summation of mod In is strictly less than epsilon. Note, hence E is a set of major 0 if given epsilon greater than 0. E can be covered by a union of open interval whose total length is less than epsilon. And second note is, it is easy to see that set consisting of one point is of major 0. Let us take theorem. This is actually property of set of major 0. If each E1, E2 and so on of R is of major 0, then union n runs from 1 to infinity En is also of major 0. If each E1, E2, En is of major 0, means what? E1 is of major 0 means what? For each epsilon greater than 0 there exists a finite or countable number of open intervals In such that E1 is a subset of union In and summation mod of In is strictly less than epsilon. Similarly for all En. Then union En is of also major 0. Means what? Union of set of major 0 is major 0. Okay. Second, write down corollary. Every countable set of R is a set of major 0. This corollary is very important, which is useful in solving problem. Every countable set of R is a set of major 0. Always remember that every countable set of R is of a set of major 0. Okay. Let us see one example. Example 1. If A is not of major 0, if A is not of major 0, if B is a subset of A and B is of major 0, okay, prove that A minus B is not of major 0. A minus B is not of major 0. Solution. Here we have to prove that A minus B is not of major 0. Prove by contradiction. Let it possible A minus B be of major 0. or we can say that assume that A minus B is of major 0. Now A can be written as A minus B union B. Okay. By hypothesis, B is a subset of A and B is of major 0. By hypothesis, B is a subset of A and B is of major 0. B is of major 0. Therefore, by and also our assumption is this is our assumption, A minus B is of major 0. Here write down our assumption is A minus B is of major 0. Therefore, A minus B union B. See here, B is of major 0 and our assumption in A minus B is of major 0. That's why union of two sets of major 0 is major 0. This is by theorem. Major 0. Is set of major 0. But A minus B union B is equals to A. That implies A is of major 0. Is this possible? No. Because our assumption is A is not of major 0, which is contradiction to A is not of major 0. Hence our assumption is wrong. Therefore, A minus B is not a set of major 0. This is also one of the useful results for solving the problem. If A is not of major 0, B is a subset of A and B is of major 0, then A minus B is not of major 0. Okay. Let us see here one more example. Example 2. Prove the following. First, the set of rational numbers Q is of major 0. The set of rational numbers Q is of major 0. And second one is the set of all irrational numbers. The set of all irrational numbers is not of major 0. Is not of major 0. Solution. First, we have to prove that the set of all rational numbers Q is of major 0. Okay. Since we know that Q is countable, set of all rational numbers is countable. Okay. As previous, we have seen one corollary. Every countable set of R is set of a major 0. By using that corollary, the set Q of all rational numbers is of is set of major 0 or is of major 0. Okay, this is first. And now see second. The set of all irrational numbers is not of major 0. Why this is? Because see here, we will compare this problem with this example. Okay, how to prove this? Suppose here we will take B set is Q and R set is set of real number. Okay, we know that R is not countable, that's why R set R of all real numbers is not of major 0. The set R of all real numbers is not of major 0. Okay, Q is a subset of R is of major 0. Q is a subset of R is of major 0. Therefore, see here, R is not of major 0. Q is a subset of R is of major 0. Then Q complement. Here A minus B is nothing but B complement. Okay, because B is a subset of A. Q complement is equals to R minus Q is not of major 0. Students, always remember that set of rational numbers is of major 0, but set of all irrational numbers is not of major 0. Also remember that set of all real numbers are also not of major 0. Okay, student, write down note. First is every subset of a set of major 0 is also a set of major 0. Every subset of a set of major 0 is also a set of major 0. And second one is if f is continuous on closed interval 0, 1 and if f of x is equals to g of x, almost everywhere x is belongs to closed interval 0, 1, then g is continuous almost everywhere, then g is continuous almost everywhere in closed interval 0, 1. F is continuous on closed interval 0, 1. And if f of x is equals to g of x, almost everywhere means what? Not continuous everywhere in closed interval 0, 1. Then g is continuous almost everywhere in closed interval 0, 1. Okay. Now we will take the definition of this function, continuous almost everywhere. Definition: a statement is said to is said to hold at almost every point of closed interval AB, or almost everywhere in closed interval AB if the set of point of closed interval AB at which the statement does not hold. Students, just remember that function is continuous almost everywhere in point of closed interval AB means what? It is continuous at some point in closed interval AB, but not at every point. Okay? Student, next see some more definition. Let I be any bounded interval. Let I be any bounded interval of real numbers and let F be bounded real valued function on I. We define capital M of Fi and small m of Fi and omega of Fi as capital M Fi is equals to least upper bound of f of x belongs to I. Small m Fi is equals to greatest lower bound of f of x such that x is belongs to I, and omega of Fi is equals to greatest lower bound of f of x belongs to I. Sorry, here capital MFI minus small mfi. Capital M of Fi minus small mf of I. Okay, this is the oscillation. Okay, capital M is this. Capital M is least upper bound of f of x. Small m is greatest lower bound of f of x, and omega of f of I is equals to capital M Fi minus small m Fi. Okay, these two are very useful definitions. Let us write down next definition. Definition is of subdivision. Now we will see what is subdivision. Okay, subdivision of the closed bounded interval AB, we mean finite subset, a finite subset x0, x1 and so on up to xn of closed interval AB such that A is equals to x0, which is strictly less than x1, x2 and so on up to xn, which is equals to B. If sigma and tau are two subdivisions of closed interval AB, we say that tau is refinement of sigma if sigma is a subset of tau or tau contains sigma. Okay. If sigma is equals to x0, x1 and so on up to xn is a subdivision of closed interval AB, then closed interval I1 is equals to x0, x1. I2 is x1, x2 and so on up to In is equals to xn minus 1, xn are called the component intervals of sigma. Subdivision of the closed interval AB, we mean finite subset x0, x1 and so on up to xn of closed interval AB such that A is equals to x0, which is strictly less than x1, which is strictly less than x2 and so on up to strictly less than xn is equals to B. If sigma and tau are two subdivisions of closed interval AB, we say that tau is refinement of sigma if sigma is a subset of tau or tau contains sigma. Okay. If sigma is a subdivision of closed interval AB, then closed interval I1 is of these two elements. Closed interval x0, x1, I2 is x1, x2 and so on up to In is equals to interval xn minus 1, xn are called component intervals, okay, of sigma. Let us take one more definition. Upper sum for corresponding F corresponding to subdivision sigma. Let F be bounded function on the closed bounded interval AB, and let sigma be any subdivision of closed interval AB. We define UF sigma called the upper sum for f corresponding to sigma as uf sigma is equals to summation k runs from 1 to n capital M F I K into mod I K, where I1, I2 and so on up to In is component intervals of sigma. Similarly, the lower sum is LF sigma, which is equals to summation k runs from 1 to n capital M F I K into mod I K. Okay, students, here these are the very important definitions. Upper sum for f corresponding to subdivision sigma, that subdivision, any subdivision. Let f be bounded function on the closed bounded interval AB, and let sigma be subdivision of closed interval AB. We define uf sigma called upper sum for f corresponding to sigma as uf sigma is equals to summation mfik into mod ik over k runs from 1 to n, and lower sum is nothing but, here is small mfik into mod ik. Okay, students, always note that upper sum for f is always greater than or equal to lower sum for f if sigma is subdivision. Remark, uf sigma is always greater than or equal to LF sigma. Sigma is subdivision, any subdivision of closed interval AB. Sigma is not. Okay. Now see example 1. Consider closed interval 0, 1. Let sigma and tau be two subdivision of closed interval 0, 1. Let sigma is equals to 0, 1 by 3, 2 by 3, 3 by 3 is nothing but 1, and tau is equals to 0, 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, 6 by 6, which is equals to 1. Students, here observe that sigma is a subset of tau, or tau contains sigma. Okay, therefore what? Therefore tau is refinement of sigma. Okay. Let us take one more example. Example number 2. Let f of x is equals to x, 0 is less than or equal to x is less than or equal to 1. Okay. Let sigma be the subdivision, let sigma be the subdivision of closed interval 0, 1 and sigma is equals to 0, 1 by 3, 2 by 3, 3 by 3, which is equals to 1. Compute UF sigma and LF sigma. Compute UF sigma and LF sigma. Okay, solution. We have f of x is equals to x. We have given function f of x is equals to x. Sigma is equals to this subdivision of closed interval 0. We have to compute UF sigma and LF sigma. Okay. For that, as previous, we have seen the formulas. Okay. First of all, write down what we have given. Sigma is equals to 0, 1 by 3, 2 by 3, 3 by 3, which is equals to 1. Okay. We know that UF sigma is what? We know that UF sigma is nothing but summation MF IK into mod IK. Okay, but here we make 3 intervals, that's why K runs from 1 to 3. Call this equation number 1, or here we can say K runs from 1 to n. Okay, let here I1 is interval 0, 1 by 3. Therefore, mod I1 is 1 by 3 minus 0, which is equals to 1 by 3. I2 is equals to interval 1 by 3 minus 2 by 3. Sorry, interval is 1 by 3 comma 2 by 3. Therefore, length of mod means length of I1. Length of I2 is 2 by 3 minus 1 by 3. It is again 1 by 3. I3 is equals to 1 minus 2 by 3. Therefore, length of I3 is again 1 by 3. Okay. To calculate UF sigma, first of all, we have to calculate MF IK. So, MF, here component intervals are 3. For each component interval, we will calculate capital MF IK. Capital MF I1 is equals to least upper bound of f of x. X is belongs to I1. Here, least upper bound of f of x is x and x is belongs to I1. See here, this x is belongs to I1. Our function is x. Now, what is least upper bound of I1? It is 1 by 3. So, put here x is equals to 1 by 3. So, we will get MF I1 is 1 by 3. Okay. Similarly, we will calculate capital MF. Here I will write capital MF I2. Don't write here. MF I2. What will be the MF I2? It will be least upper bound of f of x is x. X is belongs to I2, which is equals to, see here, least upper bound for I2 is 2 by 3. That's why this is 2 by 3. Similarly, we will calculate MF I3. MF I3 is nothing but least upper bound of x. X is belongs to I3. Here I3 is 2 by 3 comma 1. Here least upper bound is 1. So this is capital MF I3 is 1. Okay. So equation 1 becomes, therefore equation 1 becomes, what we will get? UF there are three components here, intervals. That's why we calculate up to k is equals to 3. UH sigma is equals to, if we put k is equals to 1 in this equation, we will get mf I1 into mod I1. What is mf I1? mf I1 is 1 by 3 into mod I1 is 1 by 3 plus. If you put k is equals to 2, then we will get mf I2. mf I2 into mod I2. What is mf I2? It is 2 by 3 into mod I2. Mod I2 is 1 by 3 plus. If we put k is equals to 3, we will get mf I3. mf I3 is what? mf I3 is 1 into 1 by 3. Okay. Now compute this. This is 1 by 3 plus 2 by 3 plus 1 by 3. Okay. Sorry, here is 1 by 9. Okay. So this is 1 plus, take LCM, 1 plus 6 plus 3 upon 3. This is nothing but here is 9, which is equals to 1 plus 6 is 7 plus 3 is 10. 10 by 9, which is equals to, sorry students, here is 2 by 9. So this is 2. This is 6 by 9, which is equals to 2 by 3. Okay. This is UF sigma. Okay. Now we have to calculate LF sigma. For LF sigma, our formula is capital L F sigma is equals to small mf ik. Suppose call this equation number 2. Here we require small mf I1. So here is greatest lower bound of f of x such that f of x, sorry, x is belongs to I1. Here greatest lower bound is 0. That's why mf I1 is equals to 0. Similarly here small mf I2, here is again greatest lower bound of x such that x is belongs to I2. Here greatest lower bound is 1 by 3. So this is 1 by 3. And small mf I3 is nothing but greatest lower bound of f of x such that x is belongs to I3. So this is 2 by 3. Now put all these values in equation 2. So equation 2 becomes mf I1 is 0. No need to multiply mod I1 because it becomes 0. Plus mf I2 is 1 by 3 into mod I2 is 1 by 3 plus mf I3 is 2 by 3 into 1 by 3. This is nothing but 1 by 9 plus 2 by 9. This is nothing but 3 by 9, which is equals to 1 by 3. Okay. So LF sigma is equals to 1 by 3 and we will get UF sigma is equals to 2 by 3. So students, here observe that UF sigma is greater than or equal to LF sigma. Okay. Students, take one example for the homework. Let f of x is equals to x. Next, to be the subdivision of closed interval 0, 1, where tau is equals to 0, 1 by 4, comma, 2 by 4, comma, 3 by 4 and 4 by 4 is equals to 1. Okay. This type of examples are very simple. We have to just remember the formulas of LF sigma and UF sigma. Okay students, we will stop here. Thank you.